This is Solve It for Kids.
Hello, my amazing and curious friends. My name is Jennifer, the Dean of all things STEM and STEAM, and this is the 8th season of Solve It for Kids, the podcast that gives kids and families a peek inside the real world of scientists, engineers, and experts as they solve problems in their jobs using creativity, cooperation, and critical thinking. And now please welcome to the show my podcast partner, Galactic Space Geek, Jeff Gagne.
Hello, Jennifer, and hello, listeners. What better way to start off a new season of Solve It for Kids than talking about the tiniest of things?
So what problem are we solving today?
How do you study the smallest things?
How do you study the smallest things? This is going to be a really fun episode. Who is our guest today, Jeff?
Our guest today is Dr. Katy Grimm. She is an associate professor of physics at Cal State University East Bay, and her research is done at CERN.
Welcome to the show, Dr. Katy.
Thank you. It's great to be here. Thank you.
Well, we are so excited to have you, of course, because you do physics, which I love physics. Physics is one of my favorite sciences, and you do such cool stuff. But what I want to know is, when you were a kid, did you ever imagine that you would be smashing things at CERN one day and learning all about physics?
No, I had no idea that this was a thing you could do.
I was going to be a little concerned if that was a yes.
Right. No, I guess when I was little, I didn't know what I wanted to be, but I was always into like space. I was always into like sci-fi. I liked Wrinkle in Time and Star Trek and stuff. And I had good math teachers. I always thought math was fun. Then later, I guess when I was going to college, I was thinking I would do earthquakes. I grew up in California. I really liked earthquakes. So I started taking some classes for that at school. Okay. Let me tell you, it is so complicated.
Really?
Yes. But as I was studying earthquakes, I had to take, regular physics, not geophysics, but regular physics. I really liked how they break everything down to really see like what's fundamentally happening and all stuff, everything around us. And then I got into particle physics, which is like really what's inside the atom, what are the smallest things? And then you're down to like super simple stuff. Like there's only 17 particles in the whole universe, compared to like what's going on with the Earth's crust, which is so complicated. I was like, okay.
I think my head's about to
once
explode.
You get down to that level, it really is.
Yeah. I mean,
really at the sci-fi
17 particles? That's it?
That's it. In the whole universe. That's how you make every single thing in the universe, is with the little combinations of those 7. Imagine if you only had 17 Legos, but you could make the whole universe.
Okay, well, this might be our shortest episode ever. Oh, wait, we just had a particle physicist tell us, it's simple.
Exactly.
Okay, so when you thought it was going to be earthquakes and you started taking some of those classes, did you accidentally wander into a particle physics class? How did that switch happen?
Almost. You have to take a lot of like the building blocks, the fundamental physics classes. And so as I was doing that, I was also taking some geology stuff, which I do like. But then I did hear about this particle physics, particle astrophysics. So I took that too. And it really grabbed me. It's like really has a sci-fi element. Like once you get down to things that are that small, it's not like our normal world. And so then I was I was like, this is basically like A Wrinkle in Time, but it's real science. So,
oh my gosh. So can you explain kind of what you mean by that? Like, what do you mean that it doesn't work at the same level when down there?
Once you get into really, really small stuff, then there's quantum mechanics, which means that people noticed when they were measuring these things that things don't quite exist in space in the same way as objects in normal everyday life. You try to measure something that's really small and it moves, or it's not measured enough times and you realize it's not really there at all. Maybe it's just sort of a chance. You have a chance of seeing something. Everything is like something might be there. You have to roll a dice, and then depending on what you get on the dice, it's there or it's not there. It's like all you say, it's ruled by probability at those small scales.
Whoa.
This totally sounds science fiction.
Yeah.
Yes.
Yeah.
That's complicated stuff, and I think it's great.
I was just going to ask.
Yeah.
So is that sort of weirdness about this science what drew you to it?
Yeah, I think it is. I think like once you get down to those levels and then every new thing you discover, like, what? Is this really how it works? It appears it is how it works.
Okay.
Now I'm measuring it just to be sure.
Yes, exactly. Okay. So I want to back up a little bit, and I want, just for some of our younger listeners or people who don't, know what makes up an atom, can you kind of talk us through what makes up an atom and then the parts that you're talking about that are really, really small?
Yeah, for sure. So everything is made of atoms. And just to be clear, I know like a lot of times you learn about cells, right? All living things are made out of cells. And this is even inside of that. So smaller than cells, everything is made of atoms. And even not living things like the air and plastic and metal, everything is made of atoms.
Okay.
And every atom has a nucleus. And so like the middle part, and the middle part is made up of protons and neutrons.
Yes.
And depending on how many protons there are, you get a different material. So that's like really what distinguishes different materials, is how many protons are in there. And then you can go deeper than that. You say, what's inside the proton? And now we know that inside the proton, there are quarks. And the quarks have super funny names. There are 6 different quarks, and they're called up, down, strange, charm, top, and bottom. Sometimes like the last ones are called truth and beauty. So I heard that they named them that because they didn't really think they were real. And then they found out they were real, and they were stuck with the names.
Oh, there you go.
Careful when you name something.
So if you're a kid, you're probably saying, well, what's inside those quarks? Because kids always ask that whenever I talk about this. And that is the right question to ask. And right now, we don't think there's anything inside them. We think that those are the smallest things, that if you try to break apart a quark, there's nothing. That's it. That's a fundamental part of the universe that can't be broken into something else. So there we say, okay, we made it. We found the smallest. We started at an animal, and we went into cells, we went into the atoms, we went inside the atoms, inside the nucleus, and we got to quarks, and we think that that's it. That's the smallest thing.
Okay. Now I want to be that annoying kid and ask, haven't we thought that we found the smallest thing before, but we didn't? So what makes us think that quarks are now the end of it, the smallest?
Yes, that is exactly the question you should ask. It's a little bit hard, the answers. I will say that there are many, many people looking for what's inside of quarks. There are people on it. I'm not specifically looking at that, but one of the reasons that we think that there's nothing inside of quarks is there's like a way that you can add energy to things that are made of other stuff that makes them kind of ring, or you say there's an excited state, you put some energy in, and things inside can bounce around. And we've tried to do that with quarks, then nothing happens. There's no you made that into like an excited state of the particle. So that's one hint that maybe there's not, maybe we really have made it to the bottom.
Yeah.
All right.
Okay. So now that we know that they exist, how do you study these tiny little quarks? I know you work at a pretty amazing place called CERN. Can you tell us a little bit about that?
Yeah, CERN is an amazing place. It's a big lab. It's in Switzerland, and they have something nobody else has, this or at least they have got the biggest one.
Yes.
They've got the largest collider of particles. So this is a huge tunnel, and inside of the tunnel, you accelerate protons. So these tiny, tiny things inside of atoms, you put them into a beam, and using magnets, you turn them so they're going in a circle, and you get them going really fast in two different directions. And then you smash them together. In some ways, it's like not that sophisticated an idea to figure out what's inside something. You just smash it, and then you look. But it turns out that by doing that, we can measure really carefully. And this is like, a lot of people working on how to measure what happens when you smash them together. You look at all the stuff that comes out, and then that tells you about the quarks. It tells you also, and this is where I think it gets really interesting, that moment when you smash together the protons, because you've got so much like speed coming together. You think of like two really fast things, two baseballs hitting each other with tons of energy.
Right.
That energy of the two protons puts you in like a different space that is similar to the early universe. So like at the beginning of the universe.
Oh, wow.
All of the stuff that we know now, we think was really, really close together. And so had a lot of energy really in a small space. And that's what we're creating when we smash together those two protons. So besides seeing what's inside the protons, we're also making new particles. And they're particles that only existed in the early universe when we had more energy in a small place. So we're learning about how do those quarks, how can they reconfigure and make other particles besides protons? How can we create other particles besides quarks? There are some other fundamental particles that we've made.
Wow.
And how do these things interact and then make everything we know in the universe?
Those are some big questions.
Yes.
Small things.
But she's got people working on it.
That's right.
They're working on it.
That's right.
Okay. I definitely want to go deeper. I do want to ask one sort of side question about the actual collider itself. I suppose it's a little two-part question. How do you know you're only putting one proton in at a time to go one in one direction, one in the other direction? And two, how do they not collide before you want them to? Are they on like a Hot Wheels racetrack and then you push a button and then they go?
Almost, kind of.
Yes.
They're in two different tubes. So we build a super big detector, which is kind of like a digital camera, but high. It's got a lot of layers, and you build that in one spot, and then you've got these tubes, and inside it's not just one proton hitting one proton, because you're exactly right. That would be really hard to do.
Yes.
Okay.
Huge cluster. It's like a cloud of protons.
All right.
We have two clouds coming, each one in its own pipe, and then we position the pipes and then use also electromagnetic fields to, like basically magnets, to get those proton clouds to pass through each other. And then hope that when those two clouds go through each other, that protons hit each other, or at least one, we hope. And since this might not happen, we actually have it going so it hits like billions of times a second.
Wow.
Oh my goodness.
It's kind of like electricity going. It's like, these are really small things. And so you just set them going, and then you get the clouds hitting each other a lot, very often.
Okay.
Wow.
Thank you. That was a very helpful explanation.
And because you have all of this energy, doesn't it get really hot? So you have to keep everything cool? Or how do you deal with the temperature difference there? Yeah.
Everything has to be cooled. Actually, the main reason that you have to keep everything cold is we've also got superconductors, our magnets are so strong that you want them to be really cold in order to work really well. And so we use a lot of liquid helium, liquid argon, liquid nitrogen, a lot of cold substances to keep everything moving super efficiently.
Right. And you should also mention that this is underground too. So, and when it's running, like there aren't humans down there, anybody.
No. Yeah. You don't want to be down there when it's running. So it is 100 meters underground. if you want to go down, you have to take an elevator, and it does feel like it is a sci-fi experience going down into that big tunnel.
I mean, it was. So when I went there in 2019, I was able to go in the Alice detector, not where you work in the Atlas experiment, but we had to get weighed. Like you step on the little tiny elevator by yourself.
Yeah.
And they weigh you when you go down and weigh you when you come back to make sure that you don't leave anything down there, which could damage this, I don't know, 100 million, billion, whatever, however much this detector costs.
You don't want any metal down, like if you drop an earring or something and then
Yes.
super magnets.
That was really cool because you had to you had to step through the detector and they weighed you and then you went down a normal elevator, but you had to step through this little, like a tiny little phone booth. I was like, okay, I'm a little claustrophobic. Hopefully I'm not in here for very long.
Just for a moment.
Yes, it was easy. It was easy.
So when these two clouds collide, can you describe what you see?
Yeah. So it used to be in the early particle detectors, like in the 70s, say, and even before, like 60s, 70s, that you would take a picture. So you would collide your particles, and then you have to have some way of seeing what comes out. And the way they used to do it was you could make a bubble chamber. So you could make some very pressurized gas. And if a little particle went through your pressurized gas, it would leave a little very cute trail of bubbles through the liquid, and they would take a photo. And you would analyze this path. So you take advantage of the fact that a lot of particles will spin if they're in a magnetic field. So you set a big magnet in front of your detector, and then you look and you check whether your little trail of particles went straight, and that means it's a neutral particle, or if it did a loop, and that means it's a charged particle, like an electron or proton. So initially, a lot was learned by looking at these photos and then analyzing based on the direction that particles went, how much they turn in the magnetic field. So they would spin at a different spiral if they weigh more or less. And then you can tell what types of particles. There's only a few things that distinguish elementary particles. It's either how much they weigh, their mass, whether or not they have an electric charge, and then how they interact with each other. So some particles live for a moment and then decay. So there's a heavy version of the electron called the muon. The muon comes along, so you would see a little track of the muon, and then all of a sudden it was split in two. And then that was a particle that decayed into another particle.
Wow.
And you could figure out what the masses of them were. And then you learn we just produced a muon and it decayed into an electron. And we're doing that now, but not with film and a camera, but instead with a lot of sensors. But it's the same idea.
Okay.
So is that how you came up with determining that there were the different quarks? Is you just kind of looked at the output and then someone literally, as you said, just named them? They're like, okay, this one goes here. And so you'd see a pattern, right? Every time, and you just come up with the names.
Yeah, you distinguish them. Their only difference is how much between the quarks is how much mass they have. So you measure the masses. The up and the down quark, those are the quarks that are in all of normal matter. So the proton is two up quarks and one down quark.
Okay.
The down quark is two down quarks and one up quark. Then you have a neutron, and then you can make all of chemistry. Okay, you need the electron to put in the electrons. And then chemistry. There's also the way that the proton sticks together and the neutron sticks together. So those three quarks are stuck together with a gluon. And that's the strong force. It's like this weird particle that's named gluon because it sticks together.
Well, that's an appropriate name, right?
Yeah. So that's all of normal matter. And then if you have yourself a particle accelerator with a lot of energy, or maybe you lived really early in the early universe when it was a lot of energy in one place, then you could encounter these heavy quarks like the strange and the charm and the up and the down. Those ones have higher mass, and so you need a lot of energy to create them.
Oh, wow.
So you would discover them by measuring their mass, figuring out how they're turning in this magnetic field, figuring out what their mass is. And you say, oh, this is not an up quark. This is a beauty quark. It's very heavy.
So with your research studying this, do you have a target? Do you have a goal on what it is you are trying to find?
That's a good question. So for a long time, we were trying to understand about this question of mass. So I said that one of the only things that distinguishes the particles is what their mass is, how much they weigh. And the sort of, when you write down the equations that describe all of these particles, that's one of the benefits of quantum mechanics, is you can really write down a little equation that describes every single particle. And then you can put those equations together and you can predict what's going to happen in your accelerator.
Wow.
Which is super cool that it works.
Yeah.
In the future, basically. And that all works, except that people didn't understand how to predict what the mass would be, or they didn't even understand, even once you measure the mass, they didn't understand how did the mass get in there. It just didn't fit in with the equations. So somebody came up with a theory that if, in fact, we talked about this magnetic field, if there's actually another field all over the universe, I'll call the Higgs field, and all of the particles could be interacting with that field, but in different amounts, and that different amount is the mass. If we include that extra field in all of our equations, everything works. Then we can predict the future. So people say, okay, that's a good idea, but how could we prove it? And then it turns out that if this field were to exist, it would come along with a new particle. So besides these quarks and the electrons, would be another particle, which was called the Higgs boson.
Yes.
Called the Higgs boson. And we found that. So we were looking for that for a really long time.
Yes, I remember.
And then we found it. So now we can say that that's really a thing, that there is this other field out there in the universe. And when particles interact with the field, it creates this thing that we call mass. And that's what distinguishes all the particles. And that's the thing that really makes a difference between a proton and a neutron, a difference between all of chemistry, really.
So let me go back to the beginning. This is easier to understand than earthquakes.
I'm just saying that it's very building blocks, You put all these things together and then you make something. Whereas you have to do a lot of, with the earthquakes, you're like, well, if we could assume that
everything shifts. No, that's true. I mean, it's true. There's way more variables, I have to imagine. But okay, so
way more variables.
I do think you did a really good job of explaining this too, by the way. But if there's a kid who's interested in what you're doing, what would you say to them? How would they kind of get into doing particle physics?
Oh, yeah. Well, you could, it has a lot of math. So, if you can sort of get yourself interested in math, or, even if you're not, that could always come later. You could see if there's somebody at a local university who's doing particle physics, because most universities do have somebody doing particle physics. And then they can often maybe give you a little sneak peek.
I like that. I like that idea.
What's going on with the current particle research? There's also, of course, just noticing what's going on in nature around you is basically the best training to become a scientist. So, you're out on a walk and you just notice, what's around me? What are these things made of? And how is it all working? And looking up at the stars and thinking about, is that a satellite or a planet or a star, and what's going on up there? And I think just being really aware of the natural world around you, that is you're on your way to being a scientist there.
That's fantastic. Yeah, I like that.
All right. So I want to go back to our specific question. How do you study the smallest things? Right now, in my mind, I am thinking of a grain of sand or a single grain of, say, sugar, table sugar. How small are we talking about?
Yeah. So inside of sugar's a good one. It's because it's made of little crystallized pieces, right?
Yes.
Okay.
And those crystals are made of atoms.
Okay.
And then each of those atoms has inside of it the nuclei. So there's for each one has a nucleus, and the nucleus has inside of it protons and neutrons. So I would say if you have a microscope, you can see that crystalline structure.
Yes.
Okay.
But if you want to really see the atoms, then you can't use visible light anymore. So
All
you're
right.
going to start either hitting it with something with a lot of energy, like an electron. You can use an electron microscope, and then you can start to see what's a little deeper than what you can see with a microscope.
Right.
Okay.
Regular visible light microscope. If you're really interested in what's inside the nucleus, what's inside the proton, then you need this high energy. You could think about like, how much energy would it take to break apart something? You know, you start with a desk or something. How you break apart?
Yes.
A lot of energy.
Okay.
Yes.
You get
Yes.
inside your little grain of sand or sugar, and in order to break it apart and to break apart the atoms, you got to have a lot of energy. So you need an accelerator to really pack that.
Okay.
Yeah.
And sort of the easiest thing is to smash two of them together.
Right.
And then you're getting enough energy to really break them apart and see what's inside. And at that point, you are definitely below so you could think about light. Visible light is a wave, and it has
Yes.
some, like the distance between the trough and the crest of that wave is
Yes.
quite a bit bigger than the size we're talking about. So you don't want to use
Gotcha.
visible light, because it would just would be like a tsunami going over these
Yes.
protons. So you got to get down to, we use silicon that sends out little electrical signals. So before I was talking about making little bubbles. Now we
Right.
have plates of silicon that send out little electrical signals when a particle goes through them. And so it's a little bit, I would say, I would like to like visually see what happens when there's the two clouds of protons hitting each other, but unfortunately we only get back the computer image of what happens,
Yeah.
which is output of all of these detectors.
Right.
Right.
And then you see, it's not even like what is the proton, it's like what happened when you smashed it. So it's hard to even imagine what does it mean to see inside of the proton, because at that level, when
Right.
it's the mechanics, everything
Yeah.
is moving constantly and
Mhm.
kind of coming in and out of existence, even, we think. So you've sort of left the realm of like, what does it look like, and entered an idea of like, what sorts of things are happening at that size.
Well, and how fast does this happen too? Like,
It happens super, super fast. Yeah.
so like your eye couldn't even necessarily focus on it, could it? If you saw it?
No, right. It would happen too quickly. It's like the refresh rate of your computer or something like that. You wouldn't notice.
Which is why you have the 3-story cameras set up that you send it through the
Exactly.
detector. Yeah.
Exactly.
This has been really, really so fun and I think interesting for kids to learn of all ages, because I've learned a lot too.
Oh, good.
So now we're at the point in the show where we ask our guests to give our listeners a challenge. So what challenge do you have for us, Katie?
Oh, okay, good. Well, I hope you like this challenge. One of the things I do with one of my friends who does particle physics with me is we reconstruct particle physics things with cookies and cake.
Oh, sounds good. I'm
We're
in. I'm
Keep
in.
talking.
Yeah.
I figured I would give my challenge would be to create a proton and a neutron cookie. So the way I
Okay.
like to do this is you start with some sort of base to put your proton on. I would suggest either a plain cookie or like a graham cracker or a rice cake. And then you want to put the quarks on, and you need something to stick the quarks together with. And I like to use some glue-on frosting or maybe some glue-on peanut butter, something sticky. And then to make the proton, you're going to need 2 up quarks and 1 down quark. So I like, maybe you went trick-or-treating and you have some M&Ms or something, you could use 2 of one color, and that's the ups, and then 1 of a different color, and that'll be the down.
Okay.
You could use raisins or something. And then to make the neutron, you're going to need 2 down quarks and 1 up quark. And there you have your own little nucleus. And you could make a neutron and a proton. You can make two protons. If you make two protons and you smash them together and then eat them, then you will have detected things in the same way that we do at CERN.
I love that.
All right, moms and dads listening,
Yeah.
this is science.
Yes.
Let your kids do it.
Why not? And then you get to have a nice snack after that, right?
That's right.
This sounds
What
fabulous.
a great challenge. I love it.
That is a fantastic challenge. Well, this has been such an exciting and interesting show. Thank you so much for being on Solve for Kids, Katy.
Yes. Thank you, Dr.
Oh,
Katy.
well, thank you. Thank you for your enthusiasm. It was super fun.
What an absolutely fascinating way to start a season. Talking about the tiniest of things and CERN. I gotta tell you, my brain never goes down to this level of smallness, no matter what we're talking about. But now, after this episode, I feel like no matter what we're talking about, I'm gonna be thinking about how tiny I can think about it.
Exactly. I mean, everything is so small in the world, and we never think about this. But this is why I love Dr. Katy's challenge. I mean, come on. You get to take small things and then do it in cooking, which we all know cooking and chemistry are similar. But creating a proton or neutron cookie, that sounds amazing and delicious, too.
It does. And I feel like this is a challenge that's going to be done either more than once or with multiple protons, multiple neutrons. And I think our listeners are going to be telling their moms and dads, this is important science they're doing.
Exactly. So, if you want to review how to make these cookies, be sure to go to our website, solveitforkids.com, where we'll have that information. And if you do happen to make some of these cookies, we'd love to see pictures of them. You can always tag us on our social media. We are at KidsSolve at Facebook, X, and Instagram. And also on our website, you can learn more about CERN and see some cool pictures and learn more about the amazing research that they do about really, really tiny things.
My cookies are definitely either going to be chocolate crinkle or chocolate chip, and we want to know about your flavors too.
Yes.
Until next time, you'll hear Jen and Jeff on Solve It for Kids.